Greetings and welcome, friends. Mr. Waddy and my fellow geometricians here. Today we're talking about similarity transformations, right? My man, Ernie, Pokemon Master. By the way, tweet at Ernie about all of your Pokemon questions. He's got the most awesome Pokemon advice. He's written like a wizard guide to all the Pokemon games. It's really good. It's super effective. Performing similarity transformations. So check this out. A dilation is a transformation that preserves shape, but not size. So a dilation is non-rigid, okay? So guys, we got this. Rigid transformations result in two figures being congruent to one another, in which all of the side lengths are preserved, all of the angles maintain equality, the figure itself is congruent. But a similarity transformation is a dilation or a composition of rigid motions and dilations, and it will result in two similar figures. Okay, so two figures are similar if and only if. What's if and only if tell us? Biconditional statement. Yeah, it's true in either direction. Well done, sir. So that means if two figures are geometric, then there is a similarity transformation that maps one onto the other. Or if two figures have a similarity transformation that maps one to the other, then the figures are similar. All right. So they have the same shape, but not necessarily the same size. So shape, just so you're aware, side length. We'll talk about more of this in chapter 8, but side length is proportional. Angles are congruent. Okay, so the angles will maintain congruence. Congruence transformations preserve... Oh, did I just write down exactly what... No. Blast. I should have read it, friends. Also, I don't think there's a Waddy Math Reddit page. I don't know why people aren't commenting on it more. So here we go. Let's jump into example 1. All right, performing a similarity transformation. All right, so here's a little triangle. Let's, I guess I'll trace it out kind of blue there. So let's, step 1, translate by going over 5, up 1. So for A, it's going to go over 5 and up 1. So here's... I'll undo that one there. There's my A prime. C was 2 units to the right of A, so C prime will be 2 units to the right of A prime. And I find it easier sometimes to translate one point and then get the remaining points by referencing it. What's up? Sorry. True. It's true. So let's dilate. Let's dilate. So let's dilate. This is going to be about the origin. And we're dilating by a scale factor of 2. So our end result, A prime is kind of over 1, up 2. So go over 1, up 2 again. So A double prime will be right here. B prime was over 3, up 3, so over 3, up 3 again will be twice as far from the origin. There we go, B double prime. And C prime was over 3, up 2, so over 3, up 2 again will be C double prime. So notice that this orange triangle is not congruent to the blue triangle or the purple triangle, but its angle measures are preserved, and the figure itself will be similar. Right? I just lose like 3. Yeah, that's not the most responsible thing for them to do. So here you go. You also could have done the dilation using coordinates and just multiplied each of your coordinates x and y by 2, if that's easier. Or if your grid printed poorly, for instance, you could use that strat. Question, comment. Oh, so like, could I dilate in one dimension only? Is that what you're talking about? So like if this was a 2 and this was a 1? Okay, so that wouldn't be a true dilation. That would end up being like a distortion. It would no longer be similar. It would have been like stretched out, kind of like watching a fourth ratio movie on a widescreen TV where everyone looks wide. That's what it would kind of end up doing. And so those figures would not be similar to each other anymore. Their angle measures would not maintain congruence. Their side lengths would not be proportional. But I'm sure you've seen images where, right, if you stretch it or it one way and not the other, happens. Question, comment, hi, or just hi, shout out, hi. This will be on the test tomorrow. No, I don't. No, I don't think that shows up in geometry. Although you technically have done it with graphs of absolute values or graphs of parabolas, where maybe you remember doing horizontal stretches or vertical stretches or schmooshes, I call them, where the graph ends up getting squeezed or stretched in one direction. So you have technically done something kind of like that before. All right, here we go. So I've got two figures. I want to go from PQRS, the large one, to the orange one. So I want to describe a similarity transformation. It's probably going to be multiple. It'll be a composition of them. But how could I get orange to purple in my case? Yeah, I'll start with a reflect. I'm a fan of that. Reflect. So you guys write this down. Reflect over y axis. Right? And so R would be mapped to itself. Here, I'll draw my little dashed line for the mirror. Q is 3 units away, so 3 units away over here. This would be Q prime. P was 6 units away, so 6 units away from it on this side will be P prime. S was 6 units away, so right there's S prime. And my R prime, I guess I'll call it right. So this is where I am now. Right? And now what do you suspect I do? Dilate. About the origin, you think? Yeah. It won't be on a coordinate plane in those cases. So guys, notice it does appear as though dilating about the origin would work for these. Oh, that's weird. I was like, what's wrong with the names on these? But like, because how is S prime becoming Z? You can write a pass and I'll sign it. Sorry. Right here will do. So guys, so what scale factor should I dilate by? How about you, Caitlin? What do you think? To go from the blue to the purple, it looks like 1/3. How did we know? Right, so this distance was like 3 square roots of 2 or 3 diagonals, or you could think about this as 3, 3, and that is 1, 1. I like that explanation. And 1, 1 is 1/3 of 3, 3, right? Mm-hmm. What was your question? I'm sorry. All right. It won't be on a coordinate plane. So you might have to do it with a compass or something. We might end up doing one of those today. Yeah, we'll do one today. It might not be in this video, but we can do one today. Or it'll be kind of like this next problem. Like I said, not on a coordinate plane. So guys, how about this? All right, first of all, do you believe that all squares are similar? Yeah, it seemed, internet friends, it appears as though the studio audience, the live studio audience, believes with some amount of confidence that all squares are similar. I think it's true. I think it's true, right? What are the angles in a square? They're all 90s, so the angle measures are definitely maintained. All of the side lengths within one square are the same, and so there's definitely going to be a scale factor that would be resulting in the side lengths of one square to the next still being proportional. Except this proof is going to be a transformation-based proof. And just so you're aware, yeah, kind of like proofs are going to show up. This chapter is kind of a break from the regular two-column version, though. All right, so guys, if I want to transform A, B, C, D to E, F, G, H, all right, I had to match the letters there. What do you think I should do? Let's start with a translate. Let's translate A, B, C, D by what vector? How could I get this to line up with like something over here? You could do I wouldn't necessarily do A to H because then that would land me like on this side of it. Oh, D to H would work. Yep. D to H. I could do A to E. Right, either of those. And so that would land me like here, right? So I'm gonna call that A to E. And how do I denote a vector? How do I? It's got a hat, but it's a harpoon. Yeah. Harpoon. Yeah. Super effective against water type Pokemon. All right, so so this would end up being my A prime, B prime, prime, D prime. Right, so this proof is any like instructions that I could give that would be a similarity transformation from one to the other. And if it exists, then I've proved that they're similar. So yeah, it's a little bit of a different kind of proof. You're right, yeah. All right, what do you think? Now, how could I get this blue square to be EFGH? Dilate, about what point? Yeah, about E, right? So I want to use this as my point of reference. Well, right, it has to be whichever corner they're both already mapped on. Yeah, if I had translated from here to here, yeah, then I would have dilated from there. Right, and then I'll Mario mushroom grow this square. So let's see. So dilate about point E by scale factor. Man. Guys, look at that. Someone, I don't know. Also, I don't like to eat kale. But scale factor, I was so just like caught up on scale factor is symbolized by the variable k. Spelled scale wrong. How could I figure out the scale factor? Well, check out this. Here's S and here's R. This is R as well. I want to make S over R. Yeah, perfect. Right? The new to the old. And that would end up growing this square and it'd go brr, 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 right? And it would like all, that was more of like Mario pipe sound. And so then I'd have A double prime, B double prime, D double prime, D double prime. And so I have in fact stretched that, resulting in them mapping onto each other. And then my conclusion is, right, essentially, since there is a similarity transformation, the figures are similar. Yeah? You guys believe that? Does that seem legit? Yeah? All right. I think this is when we say goodbye to our internet friends. So, class, can you say goodbye? Goodbye, internet friends.